the whole momentum and space stuff. So this is going to be a bit of a more of a silent work session a little bit at the beginning. Let's see. I just need to get some reading. It's been a bit of a long break. We'll get back at exercises as soon as we can. So, but yeah, let's just do a bit of reading, okay? I'll try to check on the chat if anyone has any comments. If not, later in the comments when it's on YouTube. But yeah, essentially, kind of what I'm trying to break, because I was working on the exercises, and sort of just the basic momentum versus pace kind of conversions, and just trying to understand the basics of like why is it that it makes sense the way is it defined. Okay, it's a very basic question. It's like, I could just go and apply the formula, right? But I just want to understand how would you even just kind of make sense of that. Like, okay, so it's like you've got something which is in position space. How do you translate that into momentum space and vice versa? So I've never come across the concept of wave vector before, and that's something that's got to do with this K, which I've seen in some of these different conversions. Uh, so I'll probably take a look into this the wave vector. I've never really wave vector is a vector which helps describe the wave. This is the very first time I've actually come across this concept. Like, any vector has a magnitude and direction, both of which are important. Its magnitude is either the wave number or angular wave number of the wave versus the wavelength. Um, okay, so you're just encoding, I guess, something that describes a wave into a vector. The wavelength is this. So the magnitude is either the wave number or angular wave number, okay, which is inversely proportional to the wave number, and its direction is ordinarily the direction of the wave propagation, but not always. Awesome. So we have not always the same definition. Okay, but let me just go through this a little bit more, because that might just be okay. So this is just a way to define a wave with a vector, and then this is got to do then something with this k-space thing here. Yeah. Okay. what's kind of not that obvious to me is this difference between sort of the spatial angular frequency and the temporal angular frequency. Because essentially, doesn't one define the other, or at least one in conjunction with other variables like the period or the, I mean, it's like if it goes faster, it's also going to oscillate more times within a unit of space, right? I mean, the same way, I guess, speed, and that is what's a bit confusing to me. So if W is the temporal angular frequency, this means how many oscillations it completes per unit of time. I guess that's a bit odd because wave essentially completes per unit of space. Special angular frequency. Isn't it the same? Isn't it somehow it must be related, isn't it? Because like a traveling wave, I guess, is there a special definition of what a traveling wave is? So yeah, it travels. So in time, that's what's confusing me a bit. So this is how many oscillations it completes per unit of time. Let's say in a second, in 1 second, right? Uh, and you know, if you say like, well, that is time in 1 second, how fast it travels and stuff like that. So in 1 second, but then that's actually what that bothers me because I don't. Um, it's the spatial angular frequency, and that is definitely I like I this is definitely I see a connection then between the momentum and the space kind of conversion stuff, and then doing this K thing in between because it's how many oscillations it completes per unit of space will definitely somehow define the momentum, right? Because that's in a way speed. Speed is sort of how many it's like how many space you cover in a unit of time, right? That's speed. What's much more complicated is frequency is like how many oscillations it completes per unit of time. Per unit of time. The question is, can you imagine so two waves with the same angular or temporal angular frequency but with different spatial angular frequency? I mean, this helps a bit because it's like from one perspective is that maybe time is that dimension, is it? If I do that, is this time? What is time and what is, like, if this is time and this is space, like it's moving, right? So how many oscillations it completes in one unit of time versus no space and time, that's not, makes no sense. Whereas in time is how many oscillations up and down goes within these. So what's drawn, like the actual thing that you see here, this peaks and valleys define the time, the temporal angular frequency, because that's like how fast you go up and down. Like if you just imagine fixing yourself one point in time, it's how fast this thing goes. Like it goes slower or faster, versus the wave actually moving like this. I think it's a bit more abstract to understand or to think about a wave just kind of moving in space or traveling in space. But yeah, it's just because it's really abstract, right? It's a bit less obvious. I'd say. I'll go back to reading a little bit, okay? Uh, what I'm struggling a little bit is the concept of it's still you think about particles, right? Emily just mentioned particles, and you mentioned the wave functions as just being ways to mathematically describe our to mathematically describe where sort of what is the position in space instead of occupying one specific spot in space. There's the wave function that defines how they occupy space, and instead of having a very specific momentum, then there's just a wave that defines that momentum, sort of. That is, I think, that is actually. But then, how do you relate those two? Is basically momentum would be, in a way, how fast that wave function of position changes over time. Wouldn't that wouldn't that be the way that you would kind of arrive at that? Because that's a relationship between momentum and position, right? It's like momentum is related to the velocity. So kind of like how fast things are. How is the position changing? In this case, is how would the how is um, the position wave function changing over time? That's how you would. To me, that seems to be just the most intuitive way of defining these. I would just go ahead and just say it's like a derivative or something like that. But it seems it's different because the formula is an integral of things, and you approach that somehow differently. So that's why I'm stuck here a little bit. I'm trying to kind of from first principles understand that. Okay, so it's even worse. I thought I got that's definitely not then the wave in which the space in which it propagates through space. That is, I don't understand this. I don't understand K. So this is essentially the phase velocity of a wave is the rate at which the wave propagates in any medium. This is the velocity at which the phase of any one frequency component of the wave travels. For such a component, any given phase of the wave will appear to travel at the phase velocity. And it's okay, but that's the relationship. That's W divided by K. Yeah. Okay. So that's like the the time angular frequency. So how much fast something in time changes versus how much in space. If okay, so if because this ratio is one, for example, right? If uh, or it would be zero if W is zero, right? If the temporal angular frequency of the wave is zero. What would that mean, though? It would mean that no, it's impossible. It can't be zero because 2 pi can be zero and t can be zero. But then it means the phase velocity can never be zero, which is also a bit odd. Um, yeah. Okay, but I've learned a couple of new things I didn't know about wave stuff. So there's the spatial angular frequency, and there's the temporal angular frequency, and then we have the phase velocity. Okay, I'll have to dig into this a bit more, definitely. Okay, so while I don't fully understand all that yet, at least I know this concept of k-space, which basically are vectors that define wave function, that define waves. Okay, so this relationship means it makes a bit more sense because now I understand what k. So if the k, so k is basically the wave vector. The wave vector is something that kind of actually has, if I understood well, the basically k is the actual magnitude of the wave vector, k, right, the spatial angular frequency, which tells you how fast the wave travels in space, in a way, right? So, or how fast it oscillates in space. I think that's important, and that is the magnitude of the vector, and then the direction tells you the direction. So that kind of, it makes sense that it's somehow proportional to the momentum vector because it's related to speed in a way, right? Wavelength to the momentum and frequency to the total energy of a free particle. Maybe this maybe I should dig into the Broccoli relations a bit more, understand, because this seem to be quite some key concepts, like they relate wavelength to momentum. So the wavelength would be then directly related to the momentum. This means the smaller, probably the smaller the wavelength, the higher, yeah, the fast, the more the momentum. And the frequency is then related to energy. That is also very interesting because the temporal frequency that defines how many energy the particle has. This is something I should somehow dig into. I think that is a bit more fundamental, but I think it's definitely, what would be the best, what's the best way to approach these? Matter wave. Maybe this is, yeah, okay, so matter waves. Yeah, okay. That could be, that's definitely something that I should go, okay. What the hell is that? Give me a second. Cool. So I think that is definitely something that I have to dig into because it's going to help me understand a bit more about the relationship between energies and this kind of stuff, and then waves and matter, and why are these things make sense. Yeah, man, that is actually, it's a key concept. It's an important thing to understand. It's like it's easy to just abstract away and like it's kind of like yeah whatever, mechanical waves and energy and stuff like that. That's something I have to definitely dig into. But okay, so this is something I should bookmark for next session, matter wave, wave vector. But yeah, so essentially, okay, this starts to make a bit more sense. So momentum is related to k, to the wave number. Um, because the terms momentum and wave vector are used interchangeably. Okay, however, that is not true in a crystal. Okay, whatever. Uh, Classical mechanics, it's the derivative, right? Hamiltonian mechanics, I should read these though. It will help me understand that. But in quantum mechanics, for the condition of weighted sums, basis states. Principles is free to choose a set of bases as long as they span the space, which is eigenfunctions. So if one chooses the eigenfunctions of the position operator, a set of basis functions, one speaks of the wave function in position space. So the basis functions, one can arrive at a number of different representations of the same state. If one picks eigenfunctions of the momentum operator as a set of basis functions, the resulting wave function is psi k set a wave function in momentum space. Okay, so that's why they use k instead of p, kind of. A feature of quantum mechanics is that phase spaces can come in different types. Discrete variable, rotor, continuous, okay, whatever that means. Table. A relation between space and reciprocal space. But still, how do you go from one to the other? That's kind of... Yeah, it's the derivative of space. That kind of... In quantum mechanics, you define that like that. That also makes sense intuitively. Eigenfunctions are... I think I have to actually go in 5. Yeah, cool. So actually, I have to leave it here. Anyway, but I did at least figure out what K is. I'm happy. I was not aware of these. Um, one more thing at a time. So that's good. And then the matter wave stuff is also an important thing to go through, step by step, step by step. I like how to, yeah, kind of like keep building the map of all these different knowledge pieces, bits and pieces here. That is going to be definitely helpful. Definitely helpful. I just don't understand yet how this makes sense. But the main eigenfunctions are, and eigenvalues are like these. It just doesn't make sense how do we arrive at the position space and momentum space? Why? How do we arrive from one to the other? There's definitely, it's the integral, and then there's the and momentum space can be expressed as what sum of orthogonal bases like that, or as an integral. And this is what I don't get. Why there's suddenly R space and then K. This is what I don't get. This is what I don't get. That's the step. That's kind of the crucial step, I guess. Or even just to understand that three-dimensional wave functions in momentum space can be expressed as a weighted sum of orthogonal basis functions. But why is it that we're multiplying with psi? That's what I don't get. Anyway, that's what I'm intuitively, I don't understand that representation. Cool. Yeah, I mean, Fourier transform. Hi Roman, I was actually about to finish and stuff like that. I have the feeling the Fourier transform is something that you kind of figure out in a way, like sort of retroactively, as in, like, I've read somewhere that it's not necessarily that the Fourier transform is like, yeah, somehow I don't know. I have quite some gaps in my current understanding of all these, so it makes it difficult for me to just drop Fourier transform and then be happy with it. I'd like to. Essentially, the Fourier transform is just something that it's like the relationship between frequency domain and time or period domain, right? I'm not so sure that helps me understand these, like, just even these. Just forget about the integral stuff. Just these. Like, why is that? I don't understand at a fundamental level why are multiplying psi, which is then space, with the basis functions, eigenfunctions of K space or momentum space. I need to somehow open that box. That's what I'm. Coefficients of the series. But I'm not so sure why. I'm sorry. Yeah, I have to actually go. So, but I'll do another one tomorrow. Hopefully, dig into this a bit more. Thanks for the comments. See you tomorrow.